In the previous chapter, we learned about the atom, and specifically what I'm thinking about is the location of the subatomic particles with the protons and neutrons in the nucleus, in the center of the atom, and the electrons in the electron cloud. In this chapter, we're going to learn about modern atomic theory as it relates to the location of the electrons. The goal is to learn about ways we can understand the location of the electrons that will help us understand bonding, which we will encounter in the next chapter. Now, modern atomic theory is mathematically based, and I do not plan on going through all of the mathematical equations with you in this course. If you take the next level of chemistry, you will start seeing some of the mathematical equations associated with this atomic theory. Instead, for this class, I wanted to take the approach of we are going to get the fruit of the atomic theory. And you might say, what? Well, I kind of think about it like if I needed to buy some apples to make an apple pie, I could go to the grocery store and get the fruit, right? So I can go buy the fruit to make my pie. So I have a basic understanding of how the fruit got to the grocery store. I'm sure there's details and things I don't know. There's probably more difficulties than I realize, but I kind of know how the apple got there. I know it just didn't pop there, right? And then I can get the fruit and make my apple pie. Well, that's how we're going to treat the electrons. We're going to kind of get an idea, an overall view of the concept, some of the progress that was made, get an overall view without diving too deep into the mathematical component. And we're going to get the fruit from the atomic theory so that we can take that forward and use that to understand bonding. Okay, so let's start. So the place to start when we're understanding electrons is waves. And there's two reasons we have to look at waves. One is because they discovered that the way they can explain light, which moves in waves, can be helpful in explaining electrons, which I'll mention again. The second reason we have to understand waves is that light, which moves in waves, interacts with electrons. And so that interaction also helps them understand electrons. So we have to know a little bit about waves. And again, there are mathematical equations for everything that I'm saying, but we're going to try to look at waves conceptually. So when we say wave, a wave in of itself is this purple line going up and down and up and down and up and down. That's what we're talking about, a wave. And on this slide, there's some properties that we will talk about in subsequent slides. One of them is the wavelength. And that little symbol there is a Greek letter lambda. So the wavelength is the distance between the peaks or the troughs of a wave. So the peaks are the top. So the distance between two consecutive peaks, that would be a wavelength, which would be equal if you measured what they call the troughs or the lower point. So those would be, for this particular wave, this is the same distance. Okay, that's the wavelength. Frequency, which is a nu here, the Greek letter nu. So nu, which is N-U. That's the number of time a wave passes through a certain point, and then speed is how fast it's moving. Now, what we're going to use most in these is wavelength, because we're going to relate wavelength to energy. Okay, so when we talk about wavelength, we're going to relate it to energy, because that's what we're going to need to think about when it comes to electrons. So properties have wavelength, frequency, and speed. And the wavelength is, I'm going to write down here, the wavelength is indirectly, I'm going to use some new words here, proportional to the energy. And I'm going to, usually when I write energy, I'll just use a capital E. Now, this is the relationship we're going to have to think about. So as you think about waves traveling through space, they have different energies depending on their wavelengths. And the wavelength, how long the distance between the two peaks, that distance is indirectly proportional to the energy. So what does indirectly proportional mean? We're going to use it more than in just this chapter. Another way that people express something that's indirectly proportional, they say that it's inversely proportional. And what that means is when one of the knowns goes up, the other one goes down. They do the opposite of each other. So if wavelength goes up, the energy goes down of that wavelength. If the wavelength goes down, the energy goes up. So they're inversely or indirectly proportional. So let me show you. If I were in class, I would use my arms, but I'm going to, if you look at the top of the screen, so a short wavelength would look like this. And I just want you to move your hand through space, trying to make that wavelength here short. So make your ups and downs really close together. Then I want you to take your hands and make your hands go like this and try to make the peaks far apart. And you will see when you try to make just do it with your finger. Put your pointer out, do it with your finger, go up and down real close together. And now go up and down. You can try to keep the same speed, but go up and down far apart. And don't you see that when it's close together, that's a lot more energy than when they're far apart? Okay, so shorter wavelengths give higher energy. Longer wavelengths give lower energy. Now, how does that connect to what we're talking about? Let's look at this, what's called the electromagnetic spectrum. So electromagnetic radiation, abbreviated EMR, is a form of energy that travels through space in waves. And it's very common things that you will recognize the names of. There's a whole bunch of energy that does this. So you can see down here, there's gamma rays, X-rays, ultraviolet light, visible light, infrared, microwaves, radio waves. These are all examples of radiation, a form of energy that travels through space in a wave. Okay, and so when we look at this, on the top is the wavelength in meters. So if you look at radio waves, down here it's 10 to the 4th meters. And gamma rays are 10 to the negative 12 meters. So down here, short wavelengths would have high energy. You'll see why we have to understand this a little bit. And here, this would be a longer wavelength, would have lower energy. So let's look at the visible light, because this is what we're going to use for our electrons. So visible light is a form of the electromagnetic radiation. And we're looking right in here. So here's their wavelengths there. And so we have visible light. We have red, orange, yellow, green, blue, indigo, and violet. Some of you may have already learned this, but if you want to know all the colors of the rainbow, I was taught to think of this unusual name, Roy G. Biv. And it's red, orange, yellow, green, blue, indigo, violet. And those are the colors of visible light. So if we look at this spectrum, notice that all light, the visible light, and I'm focusing on visible light because it's what our eyes can detect. And there is some variation because not everybody's eyes detects visible light in the same way. But our eyes can detect visible light, and it's something that we can see when it interacts with electrons. So I want to focus on the visible light and think about its wavelengths and then its energy. So the red light is on the longer side. So red would have invisible light. It has the longer wavelength, and so it has, of the visible light, the lower energy. And then violet light is on the other end. It has a shorter wavelength in the visible light, and so it has a higher energy. All right, so takeaway from here. I want you to know that electromagnetic radiation is a form of energy that travels through space in waves. And one of the properties of waves is that they have wavelengths. That's the distance between their peaks. And that is indirectly, or another way to say it, inversely proportional to the energy. So if we're thinking specifically about visible light, different colors of light will represent different amounts of energy. Right? So red light has a longer wavelength, and so it has less energy than violet light, which has a shorter wavelength. Okay, because we're going to look at these colors. In the first atomic theory they had, it was the experimental, they saw colors, and it was that experimentally seeing the colors and relating it to energy that started the thought of what electrons are doing. Okay. And this math, you will do more math with this in the next level chemistry, but you could do it. It's multiplication, division, addition, subtraction. You could do this math. I know I'm skipping the math, and I don't want you to be afraid that I'm skipping the math, that you couldn't do it, but you could. Now, the other thing about the electromagnetic spectrum, so this is the same visual that I had on the previous slide, but when they were studying light and trying to explain light energy, okay, they had to use not only the description of how things act when they move in a wave, but they also had to include particle properties. So it's something called wave particle duality, which means that they, in order to explain the electromagnetic radiation, they had to use both wave properties and particle properties together. Now, I just want you to keep that in the back of your mind, because this was something that became important in trying to describe the electron. Okay, so just keep that in the back of your mind, that to describe electromagnetic radiation, which is a form of energy that travels through travels through space in waves, they had to use both waves and particle properties to completely describe what is going on. And in terms of energy, you can see here the radiation, they call those little packets of energy, that would be their particle. They call those photons. You might have heard of photons before. So they use the photons, that's the little packet of energy, which is the particle traveling through space in waves. So just keep that in the back of your mind, because we'll have to pick up on that again. So the first model of where the electrons are is something called the Bohr atom. Not boring, it's actually kind of exciting, but B-O-H-R, it's the last name of a person. Now this was a mathematical model based on experimental results. So what happens is just a step back. So with Bohr, for this model of the atom, they started realizing they needed to understand where the electrons were a little bit more than outside the nucleus. So they're still accepting the nucleus as the center of the atom. And at this point, Bohr's model is early 1900s. I still don't think they know about the neutrons. But around early 1900s, there was a tremendous amount of knowledge gained in atomic structure. And so they were investigating, what about these electrons? Like, what's going on with the electrons? So what happens is this experiment, it says at high temperatures or when high voltages are applied. So high temperatures would be like the flame tests that you did in lab. When you put the chemical into the flame, you were introducing energy through that flame into the chemical. Or a high voltage would be like a neon lamp, right? So you have gas inside the neon lamp, and then you plug it into the wall and turn on the switch. You're putting high voltage through that gas, so you're putting in the energy. So what they found is when you put high temperatures into, they were working with gases. When you put high temperatures into there, it emits colored light. Now you saw that, right? Because in the flame test, you put a little bit of the chemical in, and while the chemical was there, you were getting colored light. Whether it was red or green or lavender, you were getting red, orange, yellow, you were getting colored light. Okay, so that's what they observed. Then what happens is they would pass that light that we see through a prism. So if you can imagine, I'm just going to make, that's my light. Like you can think of a neon light. I put electricity through it. So here I'm going to take it and I'm plugging it into the wall. There's my prong. Okay, so it's plugged into the wall. And I turn it on and I get light. Now what a prism is, it's like a fancy, prisms are fancy crystals, sorry. So what happens is they take a little slit, they put a fancy crystal there, and then your eyes are over here looking at the results through a scope. It's a scope. That all this is happening in a scope. We have these in our classroom, and if the next level chemistry, you'll use them. So they put it through a prism. So the light got a little piece of light came and hit the prism. Now here's what happened. Different colors of light travel through the prism in different speeds and refraction. So what happens then is, and I'm not really doing it in any certain color, which I should, if I have enough colors on my iPad, I could. So let's see, it came out a pink one. I'm just copying what's above it. Then it's split out to a blue one. It's split out to a green one, because the prism separates, because with different energies and different wavelengths, they all don't travel through the prism the same. If you take physics and other chemistries, you'll learn more about that. And so when they would look through this separated light, basically in this scope, they see the scope, and you would look through the scope, and this is what they see. They see separated light. So while the neon light, this was hydrogen actually, not neon. They used hydrogen. The hydrogen bulb, well, the hydrogen bulb, you look at it, it looks like a neon light. It's just glowing one color. That's what your eyes see. But if you take that color and you separate it in the prism, because it's composed of different energy light within there, it separates into those different colors. Remember, the different colors that we see, all of those lights have different energies. Okay? Another example that you might practically, even though you can't see this prism, if you've ever had a crystal which you then put in the sunlight and you shine the sunlight through the crystal, it will make a rainbow on another surface on the other side of it. It's doing the same thing. The sunlight, the white light, is full of all the colors from the rainbow. And so as it moves through that crystal, which acts like a prism, the different colors travel at different speeds and refractions, and they go through the crystal and come out as separated colors in the rainbow. This is doing the same thing. It's just with hydrogen and not the sun. Okay, so this was what they were trying to explain. Why would this happen? Why do we have the different colors of light? We know that it means that different energies are being emitted because the different colors are related to different energies. Where there is no light, all of this black empty space right here, there is no light coming out in those spaces. And as they looked at different elements, they'd see that each element gave unique characteristic lines. So this was hydrogen, but they didn't all look like hydrogen. They looked different. So what Bohr set out to do is try to explain this using the electron, like as the electrons. So this is what he explained. He said that here's the nucleus. The nucleus is still in the center. And what he said is that the electrons must not be moving around where they can be everywhere, but instead the electrons are contained inside orbits around the nucleus. Okay, so he said the electron can't just be anywhere, like the electron could not be right here. It can't be in between, because when you saw those spectra, there was dark space, right? Which means there was no light. So he said it can't be here, it can't be here, not allowed. He said the only place in my theory that they could be is at these orbits. So an electron could be moving here, the electron could be moving in this orbit, and the electron could be moving in this orbit. Okay, so that's what he thought. Now, what was he, why was he connecting the orbits to the light that he was seeing? And this is really cool when you start thinking about it. So what he was suggesting is that the energy that the electrons can have is something we call quantized. Quantization of energy is a really important idea for the understanding of electrons. And what quantized means is that the electrons can only have specific energy levels. They cannot have any energy under the sun. There's only certain energy that the electrons in an atom can have. If you see the word quantity in quantized, I always think there's certain quantities of energy that the electrons can have. Now, let me give you a real-life example of something that is quantized versus the opposite of quantized would be something that's continuous. So this is, and I didn't make up this example, but I like it makes sense to me. So stairs are quantized. Because if you think about it, if this is my foot, like my foot can only be on a step, right? If I place my foot above this step, what does it do? It just falls back down. I can even skip steps up to here, but I have to land on one of the steps because it's quantized. There's only certain places I can put my foot, right? If I put it in between a step, it falls back to the closest step. Now, the opposite of that, or I guess they're complementary in some ways, would be continuous. So like a ramp is something that's continuous, because if something's continuous, I could place my foot anywhere along here. It wouldn't matter. Anywhere it will go. where a step, there's only certain places that it will go. And so what they're saying is the energy of electron is quantized. There's only certain places that the electron can be. So what Bohr was proposing with his orbits is that the electrons can orbit the nucleus at different energy levels, but only those specific energy levels. And then how did he explain the light? This is in this little diagram here. So these little lines would be like, if here's my nucleus, like that was the Bohr model, right? And so it would be like, instead of doing the whole roundabout, he's just taking, like, there's one little piece, that would be right there. And then the next orbit, he's just writing here. And then the next one, he's just writing there. So it's like taking a little piece out of the orbit. So this is what he was explaining. This part is true. Okay, so what happens is, here there's a red electron and a blue one. So I'll look at the red one. So you start with an electron. Atoms like to have their electrons in the lowest energy they can go. The very lowest we call the ground state. And what happens is, when you turn on electricity or put in a flame, you add energy into that electron. And when you give electrons energy, they move. Well, I want to move a different way. They jump up to, and what Bohr was saying, they have to jump up to one of the allowed orbits. Like, they have to go to an orbit. If they don't have enough energy to go to the next orbit or skip an orbit, then they just stay where they are. So they have to have enough energy to go to one of the allowed orbits that he had. Okay, so you put energy in, it goes up to the orbit. Here's the thing about electrons. They don't like to be excited. So they relax back down. Okay, well, you put energy in. If they want to go back down, energy has to come out. And so here we see it's relaxing back down, and we get energy coming out, and our eye, I don't like having the red eye, sorry. Our eye sees the line. In the flame tests, you were putting your chemical into the flame. That excited the electrons in the metals that you were testing for. So they got excited, but even in the flame, they relaxed back down, and the colors that you were observing was from the electrons relaxing back down to the ground state. And they would keep going in a neon light, because you're not burning it away, it's in the gas. It will just keep glowing, because as the electrons are being excited and then relaxing and being excited and relaxing and being excited and relaxing. And in a neon light, if you turn off the power, right, it all goes away, because what's required is that energy to get the electrons to go up to a higher energy level. Now, they also have in this example a blue color, because remember, the different energies give you different colors. So red light has a longer wavelength, a lower energy. So it would come out, red light comes out when the energy difference, like from here to here, is less. But blue light, it would take more energy. So here's my electron down here. We put energy in, and let's say it jumps all the way up to here. It doesn't want to be excited, so it drops back down. And when it drops back down, it releases energy. And if the energy is within the visible light spectrum, our eyes see another color. And so if you saw blue light, that light comes from a higher energy, which means the energy that it was excited or that it dropped back down to was more than a bigger distance than the red light. Because if you remember back here, here, this end of the spectra has shorter wavelengths and higher energies, and this one has longer wavelengths and lower energies. So red light would have a lower energy than something that was blue light. And so Bohr was describing, that's how his model was saying, okay, to explain what I see, the electrons, since I must be only going certain places, because when I look, I want to go here. When I look at this spectra, I just see a few lines. So there's energy coming from there, from here, from here, from here, but there's no energy where the space in between is. There's no orbits there. And if you turn this to its side, like if I turned it this way, and then I put the pink and then the blue and then the green and then the orange, if I do it that way, you start to imagine the orbits and the light going up and down between these orbits. And that's why you're seeing the colors. It really is very, I don't know. I think of these things and I think, oh my goodness. So this was around 1913. Bohr, here's the thing about Bohr, wasn't quite right. Okay, so this mathematically was moderately simple. The experiment with hydrogen worked so great, like it all fit perfectly. So then they started working with the next element. So hydrogen was chosen first because it only has one electron. And so that's the simplest system to think about, one electron moving up and down among the orbits. Then they started to try other elements, which now you're introducing more than one electron, and Bohr's model would not quite work. And so it had to go on. So Bohr's model was really great until it wasn't. And this is what I tell people. Bohr actually won a Nobel Prize. And part of his contribution was the quantization of energy of the electrons. And so sometimes I think about Bohr and I think, he wasn't all the way right, but he still made significant contribution, enough to win a Nobel Prize. So sometimes in our life, our contribution may not be the end result, but we can still make significant contribution to something, even if we aren't the one in the end that has it. I don't know. I just think it's, it's pretty amazing. And this is what I had mentioned. I just drew all over the last page, but we can look at it again. It says, how does this fit with the line spectrum? And so then the ground state would be the lowest energy. And then each line corresponds to the emission, which means releasing. When it can absorb light and energy and go up. If it emits energy, it goes down. It releases energy as the electron relaxes from a higher to a lower level, which is what I was describing. And then I mentioned this, but here it is in words. The color of the light will depend on the energy difference, so how far apart those energy levels are, because that's related to the wavelengths. So the energy is related to wavelengths, related to the colored light. Now, I will mention that electrons also, these gases also emit ultraviolet and infrared light. So you can look at those if you have the right machine, and it has similar patterns. But for us, when we use our eyes, it's the colored light that we focus on. So there's other energies that are being emitted on the electromagnetic spectrum, but the colored light is what we focus, because our eyes can be the detector for that. All right, so here was the catch. Remember I told you at the beginning, I said, remember that to describe electromagnetic radiation, that's the energy that moves through space in waves. They not only used wave properties, they had to use particle properties. All right, So that was the next step with Bohr and how they started thinking about electrons. So understanding that energy had to be described this way, they started thinking, well, maybe Bohr treated the electron like a particle, but maybe there's a wave function to the electron that would also needs to be explained. So you can see here in 1924, de Broglie, who's a French chemist, proposed that matter, so the stuff that things are made of, could either be treated as a wave or a particle. So he was trying to think in this direction. And his discussion went kind of like, if you have a really large object, the mass of that object is so large that we can't see its wave properties. But if you had something like really small, like an electron, the wave properties of matter start to become important. And so to understand the electron, we have to treat it like a particle and also with a wave function to it, because electrons are so small, the waves make a difference. So Schrodinger, and sometimes like on Big Bang Theory, you might hear Schrodinger's cat. So this is the same person. In 1926, expanded that idea. And it takes a while, doesn't it? Because Bohr was in 1913. But in 1926, he is starting to propose the wave-like properties of matters and developing mathematical equations that describe electrons having wave functions. And so this is where we land with modern atomic theory. They call this quantum mechanics, and it actually doesn't allow you to pinpoint the location of the electron, but what it does is calculates what we call the regions of highest probability. All right, so we're trying to find the most likely place that an electron would be, and that's what quantum mechanics does, and that's what we conceptually will use the fruit from to help understand bonding. So we're not doing the mathematical equations and wave functions for quantum mechanics, but we can take the results of that mathematics and apply it to our bonding. So one thing I do want to mention again, I mentioned it, but what quantum mechanics does is not pinpoint an electron, but finds the probability of the electron in space. And you'll see that while Bohr's model is often used when people just try to draw an atom with its electrons because they like to have orbits, electrons do not orbit around the nucleus. So that was one thing that was not true from Bohr, but what quantum mechanics also determined is that the energy of electrons is quantized, which means electrons can only contain certain values of energy. So that continues. All right, so this is the language of quantum mechanics is what we're going to spend our time on. And so for this particular this topic, we're going to build up to all the language, and then in class we're going to use the letters and the numbers and things that we determined along with the periodic table to start working on how do we take all this quantum mechanics and apply it to the elements on the periodic table. But we got to get the language first. Okay, so quantum mechanics. It, like I mentioned multiple times, deals with probabilities. So the equations determine the highest probability regions for electrons to be found, and they call those high probability regions orbitals. So Bohr's model had orbits. Quantum mechanics has orbitals. And if you start to look at it here, so here would be an illustration, it starts to look like the cloud. Right? And here, the little dots are where the electrons might be found. And notice that closest to the nucleus is the highest concentration. And as you go out, it gets less and less. So there's these areas where we have higher probability of finding the electron. So it's not orbits anymore, but that is orbitals, regions of high probability. All right, so in quantum mechanics, to describe the location of an electron, you have what are called quantum numbers, and there's 4 of them. Now, I'm not doing the calculations with the quantum mechanics, so they each have their own little calculation, but we have to have the results of the 4 quantum numbers. Okay, so we're going to have 4 different things that we have to think about for each electron. So I want to go through the different things that we have to consider. So the first thing is called the principal energy level. It's given an N. And if you look down here, N is going to always be a positive number, and it starts with 1. So we oftentimes draw where electrons are going like this. And so the closest to the nucleus would be level 1, then level 2, then level 3. Notice they get closer together, which is part of the math. Then level 4. And so the energy level really is indicating how far away from the nucleus that electron is. Okay, so the higher the energy level, the farther away the electron is from the nucleus. Now, I do want to tell you, which we're going to go over, these numbers all directly relate to the periodic table. So I need, principal energy level, I'm going to relate it to the location on the periodic table. And the principal energy level, again, is just telling us how far away the electron is from the nucleus. Okay. Then inside the energy level, there's something called a sublevel. So that prefix sub means below or beneath. So remember, like we said, atom, and then we said subatomic particles, which meant particles inside the atom. So in this example, we have energy levels, and then we have sublevels. So these are levels that are inside the energy levels. And the designation of the sublevels are letters S, P, D, and F. They stand for words like sharp, principal, diffuse, and fundamental, but those are not words you have to associate. I just want you to know they do stand for things. The words that they stand for, though, are not important in how we understand it for electron. What we're working toward is electron configurations. So they do stand for words, but you don't have to try to memorize those. That's why I don't have the actual words on the slide. So the energy levels are divided into sublevels. And so here I have their relationship. Whatever the energy level is, that's how many sublevels it gets. So the first energy level, which is closest to the nucleus, only has one sublevel inside of it, and that's an S. The second level has 2, S and P. The third level has 3, and the fourth level has 4. So notice they always start with S every time you go to a new level. So everybody has an S. Then whatever level number you are, that's how many sublevels, S, P, D, F. And it always starts with S, then adds P, then D, then F. Now, if you had a level 5, there's only 4 sublevels. So even anything above 4, so even 5, 6, 7, all would only have S, P, D, and F. Okay, so the energy level tells us how far. The sublevels are a part of the energy level, and they're going to contain the orbitals. That's where the electrons are. I know it's kind of crazy, but it's all math. These are solutions to mathematical problems. Okay, and I think I have this twice. So I don't know why I put it twice in there. I need to take one of them out, but it's okay. We can look at it again just to emphasize. So whatever the energy level is, that's how many sublevels it has. And the sublevels are always letters S, P, D, and F. And since there's only 4, if you go any energy level higher than 4, they only have 4 sublevels. Okay, so inside the sublevel, so we're like kind of digging deeper and deeper. So the energy level is how far away you are from the nucleus. Then you have sublevels, so like compartments. I kind of think of them, or I probably just compartmentalize them in my brain. They have these inside compartments inside your sublevel, and then the orbitals, which is actually the high region of probability. Each sublevel has orbitals inside of it. So orbitals are not orbits. Remember, orbitals are regions of high probability. So depending on what sublevel depends on how many orbitals. So everything with an S only has one orbital inside of it. And the S looks like a sphere. And every s orbital would look like a sphere. So remember, we have energy level 1. So let's see, N is the energy level, right? And we have energy level 1, energy level 2, energy level 3, energy level 4. So an S, everybody has an S. And I'm not going to draw this for all of them, but everybody has an S. Because remember, this is S, this is SP, this is SPD, this is SPD, and F. So anybody with an S has an S orbital, just one of them that looks like this. The difference is, see, this has an S too. It would still look like this, a sphere, but now it would be bigger because it's farther away. And then the S would still look like a sphere. It would just be bigger. And the 4S would still look like a sphere. It would just be bigger because you're getting farther and farther away from the nucleus. So everything that has an S has one orbital in it that looks like a sphere. And so the 1 in the 4 level, which we call a 4S because it's in the 4th level, is bigger than the 1 in the 3rd level, which we call a 3S. Now the P sublevel, remember there's S, P, D, and F. P has 3 equal orbitals inside of it. And it looks like here they've drawn all 3 of them together. It looks like a flower. So the red would go together, the purple, and the blue. Those are the 3 orbitals. They look like, by themselves, they look like a little dumbbell, like that. That would be one of them. But if you put all 3 of them together, they look like a flower. Well, there is no P in the first level. No P, only an S. So the flower starts here. Now, I'll show you. At some point, we don't really draw all these because now look what it's starting to look like. Like it's just now, it would just keep going. And then if you had a 3rd level on there, like pretty soon it just looks like that. Like, because all the shapes would just be dotting. So we don't really draw all the different orbitals. They're just related to shapes. But we don't really overlap and draw the orbitals because eventually it just looks like a cloud. The Ds have 5 orbitals. And you don't have to learn how to draw these. S and P's are pretty easy to think about, but these are the D's. So there's 1, 2, 3, 4, 5 different possibilities for the D sublevel. So D's have 5 orbitals inside of them. Imagine if you overlapped all of them, it would look just like a big green mess. And then F has 7 orbitals. And they didn't draw them I got this from your textbook. They didn't draw the F. F's look very similar to what the D's look like. So if you look at what an orbital is, it says each sublevel contains a different type of orbital. S contains S orbitals. P sublevel contains P orbitals. D sublevel contains D orbitals. And F sublevel contains F orbitals. And these orbitals are where 90% of the 90% probability of when you think an electron is there, that's the space, that 90% probability that that's where you'll find that, in that space. So if you think an electron is in 1s, that shape, that would be where 90% of the probability of finding the 1s electron is, right? If you had a 4s, it would be in a different shape. So here, and I know all this is a lot of numbers. On the next slide, I tried to put it together, but this is what I think. Okay, so this is how I remembered. So you have the energy levels. That's the 1, 2, 3, 4, on like that. And then you have sublevels, and those are inside the energy levels. Now, you do have to remember the first one only has 1, which is S. The second one has 2, which is SP. The third one has 3, SPD. The fourth one has 4, SPDF. Now, those sublevels have a space in them called the orbital, and they have the same letter. So if you're in an S sublevel, you have S orbitals. Okay. If you're in a P sublevel, you have P orbitals. Now, I wish they each only had 1, but they don't. But for me, what helped me is it's an odd number. So if I'm in these sublevels, then it's odd. This has 1 orbital, then it's odd. 3, 5, 7. So that's how I remembered. So I remembered the SPDF, and then to remember the orbitals, I had to remember, okay, it's an odd number. It goes 1, 3, 5, 7. And we're going to connect all of this to the periodic table. So I hope once we do that, we have to get these things first, and then once we connect to the periodic table, I hope it kind of weaves together for you. Now, this is a question I love to ask on the exam. So if you're watching this, you will know one of the questions in some fashion or other. I always ask you how many electrons can fit into the orbital. And the answer is 2. Any orbital can hold 2 electrons. Okay, so an s orbital can hold 2. Now, one p orbital can hold 2, but remember there's 3 of them. So total they can hold 6. So let me go back. So if I could erase, I want to erase that. So just thinking of these pictures, like this space here, it's in 1 orbital, it holds 2 electrons. In the P's, there's 2 in this one, 2 in the red one, and 2 in the blue one. So in the P sublevel, there's a total of 6. In the D's, you could fit 2 in this orbital. Every orbital could hold 2 electrons maximum. So like in the D, if you're including all of the D's, it can hold 10 electrons because each different one can hold 2 electrons. Oops, sorry. They do, and we're going to do something with the electron spin here in just a little, I don't think today. We'll do it when we're doing the electron configurations. We'll do what's called an orbital diagram, and we'll come back to spin. But there's something called the Pauli exclusion principle, and if 2 electrons can fit, like if this was 1 orbital, every orbital, no matter what kind, can hold 2 electrons, and they have to go in what they call opposite spins. So, and how they represent it, you have an up arrow and a down arrow. And that's just because, remember I told you there's 4 quantum numbers, and if you could have the same energy level, the same sublevel, the same orbital, so then the 2 different electrons, they would have to have different spins. So that's how it goes. And it's hard to believe, really, if you think about it, that 1 electron in this mathematical model gets 4 numbers. It gets the energy level that it's in. It gets the number that designates its sublevel. It gets the number that designates its orbital, and then its spin. So it gets 4 numbers to describe 1 electron. Now, when we do electron configurations, we don't have to think about it quite that way, but that's where all the The S's, the P's, the D's, everything's coming in. So in this slide, I tried to fit in electrons, like total electrons with the sublevels and orbitals. So anything that has an S, remember, can only have one orbital, and every orbital can hold 2 electrons. So anything that has an S can hold 2 electrons maximum. If you're in a P sublevel, P, remember, they get to hold 3 orbitals. Okay, so each one can hold 2 electrons. So anything, a sublevel that has the P orbitals, it can hold a maximum of 6 electrons. The D's, it goes up by odd numbers, remember. D's have 5 possible orbitals. That can give you 10 electrons. And F's have 7 possible orbitals, so they can have 14 maximum. So this is the SPDF that we were talking about. And remember, it's an odd number, but they each can have this many orbitals inside. That's where the electrons are. And each orbital can, that's a test question, can hold 2 electrons. So the maximum number of electrons in each one of those levels would be this number. Notice it doesn't matter what energy levels you're in. So if you are in the second level in the P's, that can hold 6 electrons. If you're in the third level with the P's, that can hold 6 electrons. If you're in the fourth level with the P's, this is not 3 P orbitals. This is the level, the energy level. So remember, there's 1, 2, 3, 4, 5, 6. So if I'm in the third level, I still only have 3 orbitals. Everything with P has 3 orbitals and can hold 6. Periodic table is going to help us, but we got to get this first. Okay, so this is a slide I have for fitting it all together. And so what I tried to do, and so you might want to just kind of study this. So I mentioned the first thing, the principal energy level is right here. So that's how far away you are from the nucleus. And I have 1, 2, 3, 4. Basically, anything after 4 will look the same because you can only have SPDF. Now, I put sublevels / orbitals here. The reason is what I tried to do is write how many... okay, so the sublevels are the S, P, D, and F. And then remember, S's can always have 1 orbital inside of them. That's the region of high probability. P always has 3. D can have 5. And F can have 7. And so what I did on this slide is, so like S, if you notice the S only has 1 S there, that's because S can only have 1 orbital. And then I went and I took the P's and I wrote it 3 times. See how I wrote it 3 times every time? Because I was trying to represent the 3 orbitals. So not only was I saying, okay, there's a P sublevel there, I was trying to represent the 3 orbitals when I did this. And so then like the D sublevel, I wrote the D 5 times, not because there's 5 sublevels, but because there's 5 orbitals. And when you get to the F, there should be 7. So that's how I tried to indicate in this second column that you have the different sublevels, S, P, D, F, and then they each have different numbers of orbitals. So I wrote the letter more than 1 time because they can have more than 1 orbital. And then the electrons in each sublevel, if you take the letter and multiply it by 2, then you get how many electrons. And so then each sublevel I added up. So the first level only can have 2. But the second level, if if you look there, has 2 plus 6. So the second level can have a total, because this whole thing is the second level. The second level can have 8 electrons. And then the third level is S, P, and D. So each thing has these, and if you add all these together, the third level can have 18. And the fourth level, which has S, P, D, and F, and anything after the fourth level would have the same as this. If you add up all of these numbers together, you always get 32. So that's the maximum electrons in that particular one. Now, if you need this diagram clean, remember this is in your presentation slides, as well as you can back up the video and use it there too. Okay, so I think I have some practice slides now. So you can pause it and try to answer it, and then I'm going to explain it. Okay, so go ahead. You can pause it now. I'm going to keep going. Okay, so it says, what is the maximum number of electrons in a 4D sublevel? Okay, so 4D sublevel. So the 4 here, this just tells me the energy level. But I see that I am in a D sublevel. Now, if I remember, S has 1, the electrons come from how many orbitals there are. So S has 1 orbital, P has 3, D has 5, and F has 7. So a D sublevel is going to have 5 orbitals. Remember, orbitals are where the electrons are, and this is asking me about maximum electrons. If I have 5 orbitals, then they each hold 2 electrons, and so the answer is 10 electrons, so it's D. It does not matter that I'm in the 4th level. This could be 3D has 10 electrons. 5D has 10 electrons. The energy level doesn't matter because every D sublevel has 5 orbitals, and which would give you 10 electrons. Everything that has a D. Look back here. Okay, I'm going to erase this writing. Okay, there's the D's. That's a D sublevel. 1, 2, 3, 4, 5, 10 electrons. 4 D's. 1, 2, 3, 4, 5, 10 electrons. The difference between these and these is the 4s are farther apart from the nucleus, farther away from the nucleus. Okay, but a D sublevel, no matter what energy level you're on, can have maximum 10 electrons. Okay, here's another one. You can pause this and read the question, and then I'll answer it. All right, what is the maximum number of electrons that can occupy the n equals 3, so the 3rd energy level? Okay, let me think through this with you. So remember, whatever energy level you are, that tells you how many sublevels. So I would have 3 sublevels because I'm in the 3rd level. So that means I have S, I have P, and I have D. Okay. The electrons are what's in the orbitals, so I have to figure out how many orbitals. So S has 1 orbital. That is 2 electrons. P has 3 orbitals. That is 6 electrons, because each orbital holds 2. D has 5 orbitals. That is 10 electrons. If I add it together, I get 18 electrons. So the 3rd energy level can have 18 electrons. Again, looking at this slide, what we're saying is this is the 3rd energy level right there. It can have S, P, and D. And so then that we figured out this and got the 18. All right. So one other thing with electrons, and so let me just refer back to these kind of questions. I do ask these kind of questions just so how you prepare for that is become well acquainted with how everything is put together. So it could be that you have a chart like this and you can understand where the numbers come from. It could be like I did here on this problem. You reason through, how it would be. But you do need to be able to relate the energy levels, the sublevels, and the orbitals to the number of electrons in different places. Now there's one really super important type of electron, and that's called the valence electron. And the valence electrons are whatever electrons are in the highest energy level for that particular atom. And so what we're going to discover is that the chemical properties and bonding of the main group elements are directly related to their valence electrons. It's the valence electrons, the outermost electrons, which do all the bonding, which totally makes sense because they're the ones that are closest to each other. They're the electrons in the outermost part of the atom, and so they're next to the other atom's outermost electrons. So it makes sense that that's what would be involved in bonding. For the main group, or what we call the representative elements, everything with an A, actually the number in front of the A tells you how many valence electrons there are. So periodic table can help us out a lot there. And once we start doing electron configurations, I will be more specific and we will really look into valence electrons. So for right now, just keep in your mind that valence electrons are the electrons in the highest energy level in that particular atom. Oh, I have an example. I think I have 2 examples, and then we're almost done. And if you've gotten through this, bravo to you. It says, how many valence electrons does phosphorus contain? So if that's the question, all you have to do is find phosphorus, which is here. And this periodic table is so tiny, it's hard to see. But if you go to that little thing right there, it's 5. Phosphorus is in group 5A. And so a quick way to find the valence electrons is to look at that number right there. So phosphorus, which is in group 5A, has 5 valence electrons. Now we're going to get into more detail about them in electron configurations, but oftentimes that's all we need to know is how many. And if you need to know how many, look at the number in front of the A for that's the main group. Okay, so that was it. I thought I had one more slide, but I didn't. All right, so my expectations are that you would start to try to process this information. In our next class, we are going to take all of these letters and numbers and electrons and valence electrons, and we're going to see how it connects to the periodic table. So I've been using the slides that we have in Canvas, and so up through this point, the next slide that's after this one, that's where we're going to start class on our next meeting. So anything you can do to help yourself understand this up to this point will be beneficial, and then we're going to pick it up again, and if you have questions, I'll be happy to answer them. But I look forward to seeing you in class, and have a great rest of whatever part of your day you're in.